Hello, 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 hello. तर लगेच पाठवलं सर आपल्याला. ठीक आहे मग सर एक वाजता म्हटलं काही काही मुलं आता जॉईन होत आहेत. हो ठीक आहे.
सेशन चालू होने का है, 5 मिनट वेट करो बेटा। मेरी आवाज आ रही है? हेलो। Hello, good afternoon, sir.
Good afternoon.
Mohr from Civil Department. Now I'm giving some introduction to our students. I feel highly privileged to introduce Dr. Pusadkar, sir. I work in Government College of Engineering, Amravati in 2010 batch. He is in Civil Department, Government College of Engineering, Amravati. His specialization
No,
in
I'm at Nagpur now.
Okay, sorry. Sorry, Government Nagpur. Okay. His specialization in soil mechanics. Now, I request sir to please start your session. Okay, thank you, sir.
Okay. Thank you, Priti, and privileged to meet with you virtually after 10 years graduation from Amravati.
Yes, sir.
So, all dear students, already I had talked to you about introduction, index properties, engineering physical properties, engineering properties, and Atterberg limits, and so and so. So, we'll try to cover the rest of the topic today. So, I have a big task given by your institute to cover entire soil mechanics in 4 hours. It's a real difficult task. But however, it is just into a refreshment to you what you should focus in the preparation of the gate and how fast you can acquire that particular knowledge to get success in your gate score. I am audible to all? Am I audible to all?
Yes, sir.
Okay.
Yes.
Okay. So the first topic will start with the now particle size distribution curve because we had completed up to shrinkage limit in the last class. So for obtaining these grade size distribution curves, we need to do the sieve analysis. And as we know, the sieve analysis of the two types. One is the dry sieve analysis, and another is the wet sieve analysis. Why we need wet sieve analysis and why we do perform the dry sieve analysis? We know the soil is soil has two particles. One is called the fine grain particle, and other is called the coarse grain particles. So coarse grain particles having diameter more than 75 micron and the present contribution of the soil of more than 75 micron. If it is more than 50%, we call it as a coarse grain soil. So for classifying and for identifying the sizes of the grain particles of the coarse grain, you can perform this dry sieve analysis. And with this coarse grain sieve analysis or the dry sieve analysis, you can identify what is sand particles, what is gravel particle, and what is total fine grain particles. We are unable to distinguish the fine grain particles such as silt and clay, because we should know what is the percentage of sand, percentage of gravel, percentage of clay, and percentage of silt in the given soil mass. Then this analysis is required. Okay, so for distinguishing the clay and silt separately, we have to do wet sieve analysis, and that wet sieve analysis you are performing with either of the hydrometer method or pipette method. Whereas dry sieve analysis you perform with a simple sieve analysis process where you use a set of sieves ranging from 10 mm to 75 micron, arranging the decreasing orders with the say 10 mm, 4.75, 2.36, 1.18, 600 micron, 300 micron, 150, and 75 microns. And put the soil on the top of the top sieve and shake it well, and we get different particles which are retained on each of sieves, and we obtain the retained soil on that, and from that we'll get percentage passing. So once you get the percentage passing, we can able to plot this curve, which is called the grain size distribution curve, with the percentage passing on y-axis and grain size on x-axis. Whereas this x-axis grain size is in the log scale and percentage passing in the normal scale. So this is a semi-log graph which we use, and this curve which is plotted in the dark line indicates you the particle distribution curve or grain size distribution curves. And here I can distinguish, say this is the gravel portion, this is the sand portion, and this is the fine particle portions. Now, why we need to know this size of the particles, size of the particles? Because we want to when I want to distinguish what is sand, what is gravel, what is cobble, what is boulder, those are all represented by the size of the particles. Okay, and hence, so when I say the 2 mm size, 2 mm size, that is the diameter of the particles. Okay, so what we presume that the soil particles are in round shape and approximate diameters we are defining, because the opening of your sieves which we are used for sieve analysis are either circular or the square, and the inner diameter of that hole is about the size of that particular sieve. Okay, so if I after doing sieve analysis and after doing wet dry analysis, I can able to get this distinguished curve, and this curve will help me in identifying and classifying the soil. How? By using this curve, I can find out these two parameters. As I said earlier, percentage of gravel, sands, and fines, and D10, D30, and D60. What is D10, D30, D60? Are the D10 we always call as the effective diameter of the soil. Effective diameter of the soil. What D is indicate diameter, and this 10 is indicate that for below this diameter of soil particles, 10% are the fines. So when I want to find out what is D10, I will plot a line. I will plot a line from 10% passing, and wherever it cuts on your particle distribution curve, the particle size or the grain size is shown on x-axis will indicate the value of D10. So this is already I have shown is for D30. This is a 30 lines, and for this D30 line I have extended downward, and this diameter which I am getting here is a D30. So likewise, you get D10, D30, D60. These are used to find out different coefficients which will be useful for classifying the soils. So one is called the coefficient of uniformity represented by U. It is the ratio of D60 by D10. D60 by D10. Another coefficient is called as coefficient of curvature, which is CC, which is D30 square upon D10 into D60. So once I plot that curve, I will get these two values, and these two values will be helping me to identify whether the soil is well graded, poorly graded, or uniformly graded. Now here when I mentioned when the U is less than 5, the soil is said to be very uniform. Okay, so using these values, CCU and the CC should be 1, 2, 3 for well-graded soil. So if your CC value is between 1, 2, 3 and U value in the given range of this soil, we can classify the soil well-graded sand, well-graded silt, or well-graded clays. Okay. The same thing okay. So based upon this particle size distribution curve, the soil can be classified as well graded, poorly graded, uniformly graded, and so on and so. Also, what should be the shape of those different type of soils? Now, this curve which I'm showing in one, that x-axis your CU size and y-axis the percentage passing, and the curve is shown. What you see, this curve is a very smooth S curve. Okay, and what it indicate, the soil which is used for plotting this curve indicate that it contain the all diameter of the particles. It contain all diameter of the particles. It has, say, it has 0.02, it has 0.15, it has this one. So all the particles, all the soil particles are available in this, and hence this soil is called as well-graded soil. The soil which contain all diameters of the soil particles is termed as a well-graded plot. So we will get a normal S curve. Now the second plot which I had drawn, what is indicate this soil has only the soil, maximum quantity of soil of this diameter 1, because from this percentage to this percentage, the soil has passed of this particular diameter. So what it indicates, this soil has only one type of diameter of the soil particles, and hence it is called as uniformly graded soil. It is uniformly graded soil. This soil is also termed as a poorly graded soil, because if the soil is not very well graded, the soil will be poorly graded. Okay. So in the poorly graded, there are two different types, uniform and non-uniform. So that we'll later see. Say first one, this is uniformly graded. So what is indicate when I'm getting the maximum diameter of the maximum percentage of passing of the same diameter, that soil will be called as a uniform soil. Now another soil, this is also a poorly graded soil called as a gap graded soil. What it indicate? It has excess of certain percentage or certain diameter of the particles, and it has small quantity of another diameter of the particles. So it doesn't have a single size, it doesn't have all the size, but it has excess quantity of some particular diameter of the soil and small quantity of the some particles. So hence there is a gap between different particles, and it is called as a gap graded soil particles. This is and residual soils will of the that type, and predominantly when I go for the soil which is below the 75 microns are residual soils, because these are the fine particles, and how the soil is formed, that already you know, because of the various weathering agent is getting crushed and make the powder forms. Okay, and they are residing over that, and by some agents they are moving from one place to others. Okay, so this whereas the soil which is more than 75 microns are predominantly coarse grained soil particles. Okay, so when I have this predominantly fine particles, I will get this curve. When I'm getting predominantly fine particles, I'm getting this yellow curve. So there are the various type of the soils I can identify from the particle distribution curve or uniformly from coarse grain from particle size distribution curves. Okay, now this particular curve is helped me in, as I said, identifying the size of the particles. So there are various type of classification systems which are used for classifying the soil. Just like what name we have, we are representing a particular diameter of the soil or particular characteristics of the soil by a particular name. Okay, and hence that identification system has been developed. Various methods are the triangular methods or OS2 methods, these unified classification systems, that is IS method. Okay, so now with respect to this, your gate, I'm only discussing two. One is called Unified Soil Classification System, and other be called as a Indian Standard System. Okay, so this for performing classification using both the tests, you need to perform two different type of tests. One, sieve analysis, and other is finding out the Atterberg limit, that is liquid limit and plastic limits. So you need minimum these three tests to classify the soil. So suppose I had done the sieve analysis. Now to classify the soil and identify the particular type of soil, what do I know? Suppose we have these different type of soil, say boulder, cobbles, gravel, sand, silt, and clay. So how these are different? As I said, for coarse grain particle from sand onwards up to boulders, those are classified using this size. So the cobble has different size. Okay, so we'll see how to the different size. Okay, now just look at the gravel has been classified in addition into two categories, coarse gravel and fine gravel. The sand has classified into three categories, coarse sand, medium sand, and fine sand. And this is simply one chunk of silt and clay. How we'll classify silt and clay separately, that we'll see later on separately. Okay, so the boulder has the soil which is having diameter more than 300 mm will be classified as boulder. And from 75 mm to 300 mm is your cobbles. And from 19 mm to 75 mm is your coarse gravel. Whereas 4.75 to 19 mm is your fine gravels. Okay, so likewise, this coarse sand, medium sand, and fine sand can be identified. That is 2 to 4.75 is coarse sand, 425 micron to 2 mm or 0.45 mm to 2 mm is a medium sand, and from 75 micron to 425 micron is your fine sand. And the soil having size less than 0.75 mm, that is 75 micron, will be your coarse silt and clay. So we have say 0.002, that is 2 micron, is the diameter of your clay particle. So the soil below 2 micron is clay, and from 2 micron to 75 micron is your silt. So for identifying this silt and clay, we will do Atterberg limits. Okay. Now this, even though I say coarse sand soils and fine grained soil, once I distinguish between 75 micron, then whether the coarse grained soil is a gravel and sand, whether the fine grained soil is a silt and clay. Okay, so that we can distinguish coarse grain and fine grain from 75 micron sieve. If more than 50% particles are more, then it is coarse grain. If it is less than 50% particles are of the coarse grain, then it will be a fine grained soil. Then these will be classified by using grain size distribution, CU and CC already we had seen. Whereas fine grained soils, you need liquid limit and plastic limit. And from that, we'll get plasticity index. And there is one chart which is used for classifying this fine grained soil is called as a plasticity chart. So what is the plasticity? That also we will see. Okay. So in plasticity chart, they are classifying with the soil with the liquid limit more than 500 and 50 and liquid limit less than 15. So that is basically indicating the compressibility of the soil, whether soil is highly compressible or whether the soil is low compressible. So that depending upon that also we are giving some designation. Okay. So we require these two tests. Once we conduct this test and get the values of liquid limit, plastic limit, and the sieve sizes, diameters, we can classify the soils. Now, these different soils which we are identifying from this sieve analysis has been given some symbols. Okay, so as we have seen boulder, gravel, sand, silt, clay. So the gravel has symbol G, sand has S, silt has given M because sand and silt have same initial S. So that is M, where clay is C, organic soil is O, and peat is indicating by PT. Whereas liquid limit greater than 50, I could define as a highly compressible soil. So highly compressible soils will be indicated by H, whereas the liquid limit less than 50 is indicating as the low compressible soil, and the designation will be L. So this H and L will be used for only fine-grained soil, silt and clay, and for coarse-grained soils, we had seen how different graded soil particles are there. So well-graded part, the soil will be represented by W, and poorly graded will be represented by P. Now we have to make the combination of this soil along with these different symbols which we have said. Suppose when I say SW, S sand, and well for W, well graded for W. So it is indicating well graded sand. SP will indicate the poorly graded sand. Similarly, MH will indicate highly compressible silt. ML will indicate low compressible silt, whereas CH, CL, so those combinations we need to find out. And this well graded and poorly graded will be based upon this CC and CU already we had seen. So well graded soil will be classified when for gravels when CC is between 1 to 3 and CU is greater than or equal to 4. For sand, CC is again 1 to 3 and CU greater than 6. So once you are getting these values, you can say whether it is well graded or poorly graded. Okay. So such combination of two symbols can be made together to indicate wide range of that particular soil. So I defined SW, SC, SM, MH. So many combinations you can make and give find out what type of soil. Okay. This is a plasticity chart which I say use for classification system. The plasticity chart has two axis. One is liquid limit on the x-axis and plasticity index on y-axis. Now this chart is plotted between these two values, liquid limit and plastic limit. So what we get, this was straight line. One is called A line curve, and other is called the U-line curve. Okay. So the equation for this A line and U line is between Pi and LL, that is plasticity index, and liquid limit is Pi is equal to 0.73 into LL minus 20. So once I know this, I can draw this red line, and for for U line it is 0.9 into LL minus 8. Okay. Now the soil which is above these A lines are termed as clay soils, and the soil which are below this A lines are termed as the silty soils. Okay. So already we know that when it is more than 50, we call as highly compressible. When less than 50, it is called low compressible. So this silt is indicated by MH. This soil, clay soil, indicated by CH, whereas here it is indicated by CL and ML. So there is a band of the two names joined together, that is CL and ML. Suppose so this band is indicated that it is a combination of the silty and clay sand together with depending upon the low compressibility of the soil, because it is on the less than 50 side. Okay, so this chart will be useful for classifying the fine grained soil. And these are two upper bounds and lower bounds as A line and U line. So just like we have the borders on district or the states or the countries, here also the soil which is on the verge of one particular classification may contain some component from the other side soil particles. So such type of classification is called borderline classification, and these soils will given the name of combined together. Okay, so that borderline classification will be calculated. So this is a 5 to 12 is a percentage passing between 75 micron. This is a borderline case, and from 45 to 55 is a borderline case. So those will be classified by combination of those different soils. On the similar fashions, the Indian standard has recommended a method for classifying the soil. It is on the same recommendation, only the difference is the plasticity chart which we had used in Indian standard method is only a line curve, which equation is Pi is equal to 0.73 LL minus 20, and there are the US classification has made two classification, low and high, that is L and H plasticity, whereas Indian standard has made three classification: H for highly plastic compressible soil, I for intermediate compressible soil, and L for low compressible soil. So the rest of the process is same. I will not go in details that much, okay? Because this symbol system is similar to your US classification system, well-graded, poorly graded silt and clay. Only the difference is there in only the difference is there here in the plasticity chart. So H is indicated, H will be symbol for LL greater than 50. I, that is intermediate plasticity, is 35 to 50, and low is less than 35. So the range has been changed. Okay. And such combinations we can classify the soils. This is the plasticity chart which is used for Indian standard system. Hence, there is only one straight line which is 0.73 WL minus 20, and this is classification that say this is 50. So all the soil on this side will have H, and the soil between 50 to 35, this much 50 to 35 will be of I, intermediate, and below 35 is of the low. So the soil which is lying above the A lines are clay soils, and the soil which are lying below the clay lines are silty soil or organic soil. Now, how we differ from organic to silt is based upon whether the soil contain organic matters or not. So if you are getting that, you can classify this as organic, highly compressible soil. So this is a simple plasticity chart which is used for classification of the soils. Again, here also there is a border classification of CL and ML that you can identify. Okay, so these are the various symbols which I am indicating you for different names of the different soils. So it can have any combinations. Okay. Similarly, the joined together border. So GW, GP, GM. So there are different type of soils which you can combine. Any combinations you can make, but we could not. Hello. Sorry. Okay. So that is classification system. The next topic will start with the permeability. Now you are aware what is the permeability of the soil. You know the soil is porous. There are different particles, so there are voids in between the particles, and when the water is retained on such soils, definitely it will not fully retain. It will pass through the soil mass, and the property of the soil which allows the water to pass through the soil is a permeability of the soil. Now, why we need permeability? Why we need to understand this permeability? See, if I am constructing the earth dams, where I'm using the soil as a construction materials. Now, the purpose for construction of the earth dam is I had to retain the water. But if I don't find out the permeability of the compacted soil and try to retain this water, all the water, if the permeability is not good of that particular soil, the water will be seep through the dam. Water will seep through the dam, and the purpose of the construction of the dams will not be served. And hence, you have to identify the permeability of the compacted soil. You have to find out the permeability of even reservoir, because if the water is flowing to the body of the reservoir, that is from the ground surface, that will also not serve the purpose. And hence, this permeability becomes very important property for a soil purpose. So what this is what I am trying to mean, trying to say that the soil contain grains and there is a voids. So water will percolate through these voids. So it is not a straight line journey from one end to the others. It will pass as you get the flow. Okay, and this diagram indicate you the representation of this particular void and solid. Okay, so these are the minerals. So there will be a certain passage. Now, when water is flowing from one direction to the other direction, say water is flowing in this direction, okay, water is flowing in this direction. So if you look at the velocity of the soil particle V is here. Now, the velocity for this void, see here the wide area is this much, okay, so the area is different. Now area is reduced, so definitely velocity will change. So the velocity which is passing through only void is termed as the seepage velocity, where I am taking the cross-section area of only void. Okay, this obstruction of the solid particle has been removed. Here I am taking entire cross-section area. So there are two types of velocity: seepage velocity and discharge velocity. So Q, which is called discharge, is given by velocity into the area. So this velocity, which is in or out of the before soil, water passing through the soil, okay, so that area, if I multiply by the velocity, this is V, and when it is passing through voids, actual soil, Vs into AV. So whatever the amount of water is flowing from top, it will get the same amount at the bottom. Hence, the discharge remains same. So I can get this VA is equal to Vs into AV, and this seepage velocity will always be less than discharge velocity, because the discharge velocity is outside the soil particles. Okay, so that we should identify, and hence, if I know this porosity of the soil particle, I can find out what is the seepage velocity from the discharge velocity. So the relationship between this seepage velocity and the discharge velocity is Vs is equal to V upon M. Okay, so to identify this purpose, you have to understand some noting. The one is head of the water, because the water will flow if there is a sufficient head. Okay, so what is the head? There are two type of head: is the pressure head and the datum head. And the third one is the Bernoulli's law. The third will be your velocity head. The velocity head is ignored, so only two heads are coming. So the water will flow with this much difference of the head. So this delta H is a difference of the head. Okay, suppose the water is flowing from this point to this point. How it will flow? With this delta H. Okay, now this delta H is the head loss, and the how much length it has traveled, this L length it has traveled, and hence hydraulic gradient has come as I is equal to delta H upon L. I is equal to delta H upon L. So with this hydraulic gradient, the water is flowing. Now this will be used to find out the discharge Q. Okay. Now if I understand this Darcy's law, this H and I is helpful to me to understand this process. What is Darcy's law? It says the coefficient of permeability of the hydraulic conductivity of the hydraulic conductivity of the soil is the product of the Darcy's law. Now we know the permeability is the water which is flowing through the soil, the property of the water which is flowing through the soil, and hence this Darcy has given one equation. What he says, velocity, that is discharge velocity, is directly proportional to the hydraulic gradient of the soil. Hydraulic gradient is proportional to the hydraulic gradient which we had seen. So what equation I get, V is directly proportional to I. So if I made equate, what we will get, V is equal to K into I. So this K, which is a constant of proportionality, is termed as coefficient of permeability. This constant of proportionality, K, is termed as a coefficient of permeability. So the equation which we had seen, that Q, earlier equation which we have seen, Q is equal to V into A, discharge velocity into the cross-section area, total cross-section area. So if I put this value V as K into I, so if I use this earlier figure, if you look at, say, if I know I, if I know A, and if I know Q, I can able to find out the value of K. Okay, so you should able to identify what is hydraulic gradient. You should able to identify what is the discharge, what is the cross-section area through which the water is flowing. You can simply get coefficient of permeability, and coefficient of permeability is always symbolized in the unit of centimeter per second. Okay, so this is what the figure, again same figure has been replotted here, indicating you what is this delta H upon L is your I. So if I put that value, I will get the coefficient of permeability. This simple principle, if you look at even in the gate problems, there are few problems which are directly based upon this fundamental figure. Okay, now this figure has been shown the horizontal. The same figure, if I tilted, nothing will change. If I show the tilted, nothing will change. I should take L as parallel to the flow. L as parallel to the flow, not the horizontal length. Okay, that is the only difference you should understand. So you should able to measure the head at the entrance, able to measure the head at the exit. So difference between entrance and the exit is your delta H. So this delta H upon this length of water which is flowing through this soil mass is your L. So if I put delta H upon L here, the cross-section area is the cross-section area of this soil. So this is indicated A. So I get A, and if I know this Q, which is coming out of the soil mass, I will able to get the K value. This simple principle is used. Okay. Now there are this coefficient of permeability which we have seen, K. Definitely it is passing through the. It is the property of soil. Now it depends upon different soil particles, different properties of the soil particles, and this Mohr has given this equation, which is useful for laminar flow. The K is equal to ds square gamma upon mu into E cube upon 1 plus E into C. Now, if I look at these simple equations, I'm going to find out that this coefficient of permeability K is depending upon diameter of the particles. Ds is the diameter of the particles, gamma is unit weight of the particles, mu is viscosity of the soil particles, E is a void ratio, C is a constant. Okay. Now all these parameters definitely will be responsible for the shape factor. C is shape factor, so responsible for the permeability. So depending upon size, shape, void ratio, unit weight, temperature, because viscosity is depending upon the temperature, and hence temperature is also one factor which is responsible for identifying the coefficient of permeability, and hence this equation, which is equal to K27 is equal to KT into mu T upon mu 27. What this indicate? When I have to find out the coefficient of permeability at the specific temperature T, I should use this equation. What is expected that you will conduct the laboratory test at 27 degrees centigrade. Okay, so that usually doesn't happen. So today, if your temperature is 20 degree and conducting the experiment at 20 degree, I get the value of K as KT is equal to K20, and hence the standard value which we consider for the analysis is K27. And as I said earlier, that viscosity depends upon the temperature. Viscosity is dependent upon the temperature. So Vt upon temperature T and 27. So I should get the value of viscosity at certain temperature and the standard temperature. So I can identify this permeability at the specific temperature. Okay. The this is one equation which has been simply give you K is equal to 100 into D10 square. What does it mean? Okay. Now, if you look at this equation, if I make this entire term as one constant, which is represented by 100, okay. So what is this for silt that has this equation is used, that this equation is 100 and this D is represented by D10 square. What indicate D10? Already I had defined you D10. So if you know the D10, this is the approximate method for finding out the coefficient of, this is the approximate or indirect method of identifying the coefficient of permeability. Now, there are different methods which are used for finding out the coefficient of permeability. Here, laboratory methods, concentrated permeability, foliar permeability, pumping test, borehole test, and indirect methods. So already I had shown you the indirect method, that K is equal to 100 D10 square is used method for identifying the coefficient of permeability. Now, this is I briefly show you figures and corresponding equation which is used for finding out the coefficient of permeability. Now, this constant head method, what name itself suggests, the head which is applied on the soil mass to allow the water to flow through the soil is kept constant. Now, this head is kept constant. How? See here, this is the head. This is the head of water exists above the exit point. Okay, so this is the exit point. Okay, so this much is the head which causes the flow. Now I want to make this constant. How I will make? I will make by, there are three. There are different approaches. This is one approach has been shown here, that this is an overhead tank. This is an overhead tank, and this overhead tank is filled with the water, and the tap water is there, so that is continuously flowing here. And say excess water, if it is there, that will flow through the overflow. So whatever the amount of water is flowing through this soil will be added on the top. So the head of the water will remain constant. The second option is I can make this tank a very large tank and fill it with the water. Fill it with water. What will happen? Now the amount of water which will flowing through the soil sample and the area of the soil sample in comparison with the area of the overhead tank will be very small. And hence, if even 5 ml water is passing through the soil, the head of the water will not change at all. And hence, that remains the constant head. Okay. So this constant head method will be useful for which type of soil, whether for coarse grained soil or the fine grained soil. Because if the water is easily flowing through the soil, definitely it is a coarse grained soil. Now, say sand or gravels, okay. So this constant head method is useful for coarse grained soil because the water will easily pass through a given head. Okay. So what we will do, if we prepare a soil sample, measure the head and find out how much amount of water is flowing through the soil for a given time t. And if I know that time t, if I know this time t, and if I know the discharge q, amount of water flowing through the soil, I will get the coefficient of permeability by using this equation. K is equal to QL upon HAT, where is the H is the head of water which is flowing through the soil, Q is the discharge or the quantity of water flown through the tank, L is the length of the sample. This is the length of the sample, L, and A is the cross-sectional area. This is the cross-sectional area of the sample. T is the time for which the amount of water is flowing through the soil. So this is a very simple method. Understand it. It is useful for coarse grained soil. Okay. Now, if I use same method for the fine grained soil, what will happen? Suppose I had used this method for fine grained soil. Instead of coarse grain, I place the sample as a fine grain. See, under this head, if I allow the water to flow through it, it will take hours together to take out the water from the sample, because fine grained soils have very low voids. Okay, so the time travel for the water will be very large. It may so happen, suppose 1 ml water comes after 24 hours, we don't know with the temperature, the certain amount of water might have been exhausted or evaporated. Okay, so hence this method is not useful for fine grained soils. So next method which is there called as the falling head method will be useful for fine grained soil. Now here we are not measuring the quantity or the discharge of the water which is flowing through the soils. What we are trying to measure is the head loss. Okay, we are trying to measure the head loss. So this is a soil sample. Red is indicating this is a soil sample. Then these are the two heads. This is H0 and H1. That the soil sample which is placed here is a saturated. After saturation, we are allowed to flow the water through this tube. This is called standpipe or the burette. Burette, everyone know the burette. Okay, so we are filling this soil, this burette with the water, and before I start over the flow section from or open the crock at the bottom of the soil sample, I will measure this head. Okay, this head is say H0, and then I open the crock and allow the water to flow through the soils. After a certain period of time, this water level in the standpipe will reach, suppose, this level. So this is the amount of head which has been lost. Okay, so this is the amount of head which has been lost. So from H0 to H1 it has come, and the time here it was T0, it has come to T1, or say T1 to T2, T3 to T4. So likewise, you measure different head at different times and get the coefficient of permeability by using this equation, which is equal to K is equal to 2.3 A small a into L upon A into T1 minus T0 log of H0 upon H1 to the base 10. Now here this small a is the area of your standpipe. L is the length of the soil sample. Cross sectional area A again soil sample. This is the T1 is the time for the head H1, and T0 is the time for the head H0. Okay, so these at particular 0 initially, it is H0, T0, H1. So you may only these three readings are need to be taken. I will get the coefficient of permeability. So these are the simple methods. Okay. Now here these methods we term as the laboratory methods. Now you know with the soil which is expanding over the square meters, square kilometers, and we are taking a very small sample for testing in the laboratory. So the properties which we will be getting from this will indicate, will give you definitely good information. However, the integrity of the soil mass or the complexity of the soil mass which exists in the ground will not able to create in the laboratory. And hence, for the important structures such as dams, you have to conduct certain field tests, and those tests are conducted in situ and over a large area, and thereby we will get the exact content of the soil mass and the permeability of the soil. So there are pumping out test and pumping in test. The simple name indicating that pumping out, that means we are removing the water from the borewell. So it is simple. We make the two borewells, one through which water is pumped out, and the other borewell is in the observatory wells. Okay, where we observe the water level. Okay, so in this method, pumping out test, we just pump out the water. Pumping in test, we are adding water into the borehole, and see whether it is a pumping in or pumping out. The principle is very simple. Suppose I am doing pumping out test, I am removing the water from the borehole. See, initially before I start removing, the water level will be at certain ground level. Okay, so if I have three boreholes, suppose one borehole at the center and the two boreholes at 1 kilometer away from this main test borehole, so you will get water level in all the three boreholes, and that is the initial water level. When I am removing the water from this borewell, after a certain period of time, the water which has been removed definitely it will lower your water table, and that lowering of water table will continue till that make a constant. So that much, that means the soil, that soil has that much water that has been continuously flowing through the bore well, but your water level remain constant. Okay, so we will using this technique you can find out the field permeability of the soil. Okay, so this is what I said. We have this blue one is a borewell test borewell, and these two red ones are the observatory wells. Okay, so this is a water level. Now, initial black one is initial water level. After I pump out the water from the soil, from this soil, the water level has taken this shape. This is a deflected shape of your water level. Okay, this is on one side. Similarly, you will get water level deflected on this side because this is just a symmetrical portion. Okay. And here I said this method I am showing in for the unconfined aquifer. So there are two aquifers, confined aquifer and unconfined aquifer. What is unconfined aquifer? Probably you know in the geology you understood what is unconfined aquifer. So this water which is present in this soil mass is not under any pressure. Okay, so the atmospheric, the pressure at the top of this water level is the atmospheric pressure. Hence it is unconfined aquifer. If I have, say, a rock mass at the top here, okay, and the water is not going outside this well, so this definitely this will be under certain pressure. So that is called as confined aquifer. So that we'll see separately. Okay, so so just you get this deflected shape, and then you measure this head. So what measurement I required? I required this radius at which these observatory wells are placed. And what is the water level before start pumping out water, and after this drawdown curve is followed. This drawdown curve is indicating water level after the removal of water, and it become a constant. So this drop down curve will remain constant at that particular time. So if I am getting this radius, diameter, distances, I will able to get the coefficient of permeability from this equation, that K is equal to Q upon pi Z2 square minus Z1 square log of E R2 upon R1. This is based upon log E. If I convert into log 10, it is equation. Okay, so this is simple unconfined. As I said, confined aquifer, what will happen? So this is a rock mass, and the water level is here. So you know this water under this will be under pressure. Okay, so if I make a puncture here, what will happen? This water will come out at the pressure. So that pressure I have to take into account. Okay, again same matter. We have to dig two wells. Main is test well, and another the observatory wells. This water level is this one, deflected. Okay, so when I puncture it, I am getting these values. So this H, that is the height of aquifer. This is called aquifer. Okay, this height of the aquifer you should know, and then I can use this equation. The earlier equation was different. This equation is different. Q upon 2 pi H Z2 minus Z1 log of E R2 upon R1. Okay, so in detail you can go through the books where we will get all these equations. Now, how much amount of water is transferred from this well is called as the coefficient of transferability, and that is again given by the same equation. Q is equal to T is equal to Q upon 2.72 D1 minus D2 log of 10 R2 upon R. This D1 and D2 are the amount of water which has been dropped. See, this is D1 and this is D2. So those were the pumping out test. The water is removed from this soil. Now pumping in test, I am putting water into the well. So there are again two or three different types of tests: open end test, both end test. Okay. So open end test means this end of the borewell is remain open. Okay. So the pipe through which it has been dropped, that has been removed. Now this depth, okay, this depth, which is called the influencing area, is 10 or above this level and 10 or below, so that we can identify. Now, so initially this borewell is made, okay, this is the initial water level. Then I put the pump. This is the pumping unit I put. Okay, pumping unit has been put, and the water is now removing. After removal of water, what will happen? The depression will be taken place. Okay, so this situation is, and here in the one case, the water level has come up to this level. After removing the water from this one, water level has come to this level. Okay. So that will indicate how the water is flowing. So I will get the coefficient of permeability K as Q upon 5.5 RH. Okay. Where this head H is, what is this H? This H is equal to H plus P upon gamma W. That is the pressure at which we are applying, we are forcing water to inside. So this is the pump. This is the pump which I had placed here, right? This is the pump which is under the pressure P. So this water under at what head it has been pressed in, that I have to take into account, and that will be converted into the pressure head. So H plus P by W will be added here to get the value of A. Now, the disadvantage of this method is that you are putting a pipe and dropping the water. So the entire area, through this entire area, the water is flowing. So if I want to find out the permeability of the specific area, suppose this area, I will not be able to do this under this open end system. And hence there are two systems, one is single packer and double packer system. In single packer, some packing is applied at the borehole. Okay. Now this packing is applied here. Okay. And the water is pumped through this one. The water will pump through here. So this first test will be this particular area will be tested for permeability. Okay, and as so that means from the extreme, the end to the up to the packer, I can only test. I cannot test again here. Okay. So that will be done through the double packer system. Again, there are equations which you can go through. Okay, so water is flowing through. In double packer systems, I can apply the packing at the two level. One at this, suppose at this level and at this level. So now what will happen? The water which is flowing in will be transmitted only through this much area. And hence the permeability of this soil can be identified. So at particular depth, you can, if you want to find out the permeability, you can use this double packer test. Again, there will be equation. The equation you can go through. Okay. An indirect method, already I told you, this is given by the Allen-Hazen at K is equal to 100 D10 square. K is permeability in centimeter per second, and D10 is Hazen's effective size in centimeters. So I had to put this value D10 in centimeter. So you should keep this in mind, that this D10 should be in centimeter, not in mm. This is another equation given by Koznick-Kármán equation, where I need what I need: this surface area, viscosity, void ratio, and unit weight. That I can get these values. The specific surface area, KJ is a factor depending upon the pore shape, ratio, length, actual flow of the soil bed. So these are the two equations which can be directly used. But in many GATE examination, I found this first equation, that K is equal to 100 D square, has been asked as a question. Okay. There's another method which is indirect method, that I can find out the coefficient of permeability from the one-dimensional consolidation test. Okay, so suppose if I perform a consolidation test, and from that consolidation test, if I know the consolidation value, coefficient of consolidation CV, the gamma W is weight, unit weight of water, and volume compressibility MV, because these CV and MV will be obtained from one-dimensional consolidation test. And if I know this value, I can get the value of K. So this is another indirect method of identifying the permeability for the soils. The other factors which we should understand in permeability is, now the soil which we are considering, definitely not a uniform size. Okay, the soil is formed by putting layer by layer together. Okay, so definitely every layer has different permeability. Now, for the purpose of our interest, we make as a uniform or uniform permeability understanding. It is not so. Every layer has different permeability. So if you have a layered soil and each layer has different permeability, then what is the average permeability of this soil layer? Okay, so the average, to identify this average permeability of this soil, this particular layered soil, there are two approaches it has been defined. One is says that depends upon the direction of the water flow, whether the water flow is perpendicular to the layer, what is shown here. So this water is flowing, say, from ground to the bottom. Okay, suppose rainfall occurs and the water is flowing through it. What is the average permeability of this n number of layers will be calculated by the concept of flow perpendicular to the layers. And other concept is the water may flow parallel to the layers in this direction. Okay, so depending upon this two direction, your K average K. This is a KV, is the average coefficient of permeability when the flow is perpendicular to the layer, and it is given by H upon H1 upon K1 plus H2 upon K1. This H is the total thickness of all the layers. H1, K1 are the thickness and coefficient of permeability of the first layer. H2, K2 is the thickness and coefficient of the second layer, and so on and so. So simply I should know the thickness and the coefficient, corresponding coefficient of permeability of that layer. The second, I say, when the water is flowing parallel, water is flowing parallel to the layers. Okay. So when water is flowing parallel to the layer, the permeability of each layer is different. Okay. In this case, the discharge, in this case, when the flow is perpendicular, in this case, discharge remains same in all the layers. Q in is Q out. Whereas in this case, the velocity remains constant. And hence, when I put this equation, finding out the KH, that is average permeability when the flow is parallel to the layers, this is KH equal to K1 H1 plus K2 H2 plus and so on. It depends upon the number of layers you have and divided by total thickness of them. So if you remember these two equations, you will be easily able to get the permeability of the average permeability of the layered soils. Okay. So this is about permeability. The next topics we will start with the stresses. What is stress? You know. Stress, there are different type of stresses. Overburden strength, that is geostatic stress, right? And the stress due to load, maybe tensile stress, compression stress, shear stress, and so on and so. Now here we'll talk about only the total stress, effective stress, and so on and so. Now, say this is a three-layer soil. Okay, this is just three-layer soil having the thickness of the first layer is 3 meters, the second layer is 4 meters, and again third one is 4 meters. The unit weight of these soils are different. So first layer is 17, second layer is 18, third layer is again 18. And I have to find out, say, stress at point A, this point at A, point B, point C, and point D. So what is the total stress? It's simple. Gamma into H is your total stress for the soil mass. Okay. So suppose at A, depth is 1 meters. So if I multiply it by 17 into 1, is the pressure at this point A. Okay. And these are plotted. This soil pressure is similar to your water pressure. You had drawn the water pressure distribution diagram in fluid mechanics. Similarly, these diagrams are plotted for total stress and effective stress in the soil mechanics. Okay. So if I try to plot this stress variation, so say at stress at A is 17, stress at B, okay. So this has been plotted here. This is a variation. Okay, it's a triangularly varying. So that means at the top where N where H is 0, you will get the 0. value. Okay, so similarly, when I'm finding out the at B, it is how much? 17 into 3, so that will be 51. So variation is shown like that. Then this much pressure will remain there on the soil. So at this point, I have to find out this will be pressure. Now again from here, it will be, suppose I have to find out at C, it will be 18 into 4. So this will remain same, and additional pressure 18 into 4 which will be there will be added. So this plus this, that is 51 plus 18 into 4 will be 123. Is 123 is this much is the 123. Okay. Similarly, I can find out D. Now this pressure 123 pressure will remain there on the soil below this 7 meters, and this additional pressure at D point will be noted here by 2 into 1836. So that much soil I can find out. So likewise, this distribution will be calculated. Now here there is no water, so there is no pore water pressure inside the soil. This soil is dry. As long as the soil is dry, we will get the total stress. Now, in the first class we had seen with the soil may be dry soil, may be partially saturated soil or fully saturated soil. Okay. Now, when the fully saturated soil, all the voids are filled with the waters. Okay. Now, in that situation, the stress or the partially saturated soil, the partially saturated soil will also have some waters in their pores. This water presence in the voids reduces the stress. How it will be reduces, that we'll see. Now, the total pressure is equal to intragranular pressure plus pore water pressure. Now, what is intragranular pressure? We know the definition of the pressure or the stress is total load upon A. Okay, so Q upon A is your total pressure. So total stress is Q upon A. What is the load now? There are two parts. As I said, there is water and there is a soil particles. Now, when these soil particles comes in contact with each other, so the pressure which is transmitted to the contact of the soil particle is intergranular pressure. The pressure which is transmitted through the contact of this soil grain is intergranular pressure. And the water pressure which is there within the voids, because that water which is present in the voids will be under certain pressure, and that pressure we called as a pore water pressure. Hence, your total stress is become sigma dash plus U. What is sigma? Sigma is the total stress. Sigma dash is the intergranular pressure. That means what is the pressure in between the contact of the soil particles? And this sigma dash is defined as the effective pressure. Pore water pressure represented by U. So if I want to find out effective stress, I will get sigma dash is equal to sigma minus U. Sigma is the total press minus U. In case of soil, suppose if I don't know the pore water pressure, the pore water pressure measurement is done simply as gamma W into H. Suppose water level is represented at certain depth. Okay, so I will multiply gamma W into H. So I will get U value. So effective stress will be calculated as sigma minus gamma W HW. How it will be calculated, you see. So this is a diagram which is shown you. Already I discussed this. So the pore water pressure is known, and this sigma is also known. I can get this sigma dash as effective stress is equal to sigma minus U. Now here, this is another example which earlier example I had shown you for the total stress. Now here, in the same problem, suppose I had put here water level. Okay, so this is the water level. Now since this is the water level, the pressure below this water level will be two type of pressure. I will calculate total pressure. I can calculate effective pressure or effective stress. Okay. While calculating the total stress at any point over this depth, it's simply gamma into h. Gamma into h. So at this point, suppose it is 17.8 into 4. Okay, here it will be again 19.5 into 4 plus 6 plus 17.8 into 6. Okay, so that earlier addition what we have done, it has been done, and this figure is drawn, which is based upon the total stress. Okay, now as I said, the pore water pressure, this is indicate the pore water pressure. What is that pore water pressure? Pore water pressure, I say, is a gamma W into HW. Gamma W into HW, where gamma W is a unit weight of water, HW is the height of water present in that soil. Suppose at this level, at this 4 meter, what is the water level above it is 0. Hence, pore water pressure at this point is 0. So here, this blue line indicates the pore water. So this water is 0. Pore water pressure is 0. But if I immediately go for 2 meter below, it will be 2 into 9.81. Or suppose at this level, 6 into 9.81. So that amount is calculated and this is plotted. So this curve is for the pore water pressure. Now to plot the effective stress, what I will do, I will make the difference of this pore pressure and the total pressure. So at this 4 meter, it remains same. So there is no pore pressure over here. Hence, effective pressure and the total stress is same. Total stress and effective stress is same. But below this water table level, it has start reducing. Okay, and hence this total stress value minus pore water pressure, I will get, it is sigma dash is equal to sigma minus u. So once I get this value, this is the effective stress plot. This is the effective stress plot. So likewise, I can get the calculation of effective stress from this simple equation, that sigma dash is equal to sigma minus u. Okay, u is the pore water pressure, sigma is the total stress, and sigma dash is the effective stress. Now, the one condition of the sand is called as boiling sand or quicksand. What is boiling sand or the quicksand? This is not the type of sand. You understand it. This is the condition of the sand at which it starts boiling. Just like when you boil the water in the vessel, you find that bubbles are coming up at boiling level. Okay, and in this condition, the soil is moving upwards, and hence it's called a boiling condition of the sand. Or the soil is so quick that it loses its strength. It loses strength, and everything may collapse, and hence it's called the quicksand. Okay, so this is indicating here that in this situation now, this sand is coming up, is boiling, just like boiling. Okay, see this is a situation where the boiling has been taken place and the sand from the ground has come up because of this activity. Now, how this happened, why it has happened, that we need to understand. Now, earlier what we had seen, we said that suppose if I consider this point here, okay, this point is subjected to this much stress, gamma into h. This is the stress condition here. Okay, now the stress which is here, I suppose the water is flowing in this direction. Water is flowing in the upward direction. The seepage pressure, which is obtained due to this flow of water, if it is more than this overburden pressure, definitely this pressure will try to push everything away, and it will get certain canal through the voids, and the water will move away. So that means if seepage pressure is more than overburden pressure, the boiling condition could have been expressed. So as I said, quick refers to the condition and not to the material. Quicksand is not the type of sand, but is the material as condition. So two factors are required to come up quick. The strength must be proportional to the effective stress, and effective stress must be equal to 0. What is effective stress? Sigma minus U. So if your pore water pressure is equal to the total stress, then your effective stress will be 0. And if effective stress is 0, the boiling condition will take place. So the upward gradient needed to cause the quick conditions in cohesionous soils, which is equal to gamma dash upon gamma W, approximately equal to unity. The amount of flow required to maintain the quick condition increases as the permeability of the soil increases. Okay. So this quick condition can be identified if you know the specific gravity of that particular soil and the void ratio of that soil. And we will able to find out what is the hydraulic gradient at which this quick condition will occur. So this IC is indicating the critical hydraulic gradient for a given particular soil. Okay, so critical hydraulic gradient is IC is equal to G minus 1 upon 1 plus C. So if you know the void ratio, if you know the specificity of that particular soil, I will know that if I able to create that much gradient, then only the quicksand condition is active. Okay. So a saturated sand become quick or live at this gradient. This is only a condition, not the type of sand. Already I talked. Okay. So where is the necessity? The necessity is here that suppose you have you have a earth dam. Okay, earth dam is constructed. There is a head of water on the. There is a situation that boiling takes place at the foundation level. That condition cause related to the piping. But if there is a flow of water which is taken place and the sand start boiling, the percolation, the water may start flowing through it. Okay, and then quicksand condition may arise. That phenomena we called as a piping condition where critical hydraulic gradient is equal to 1. Water is flowing through the bottom of the foundation. Now to calculate the seepage through foundation, through body of the dam, I have to draw this flow net. What is the flow net? It is the diagram which draws the flow line, which draw potential lines. Okay. So flow net is a graphical solution to the equation of the steady ground flow. Flow net is an isometric medium, is a network of flow lines and equipotential lines. This is the flow. So these are say flow lines. The flow lines and equipotential lines are perpendicular to each other. So the channel between these two flow lines is the flow channels. Okay. So delta Q is a discharge which is flowing through these channels, and these are equipotential lines which are perpendicular to the flow. Okay. So if I able to measure the potential drop or equipotential, this potential drop or the head loss between these two equipotential lines, and I will be able to measure the quantity of water which is flowing through it. So these flow nets will be helpful to me for finding out the discharge through the soil mass and finding out the exit gradient. Okay, so that also is a purpose. So this is the one diagram which I'm showing as a flow net. This is a sheet pile. These are mild sheet piles which is inserted here, so that the water will be retained on this side, and this area will get for construction. Say this is a caisson or the caisson which is used for construction of the bridges in the river. So they want some dry place here, so they will put the steel pipe surrounding the area. So the water will be there on outside like this, but this area will be a dry place, so they can do the excavation for foundation and construct the foundation. So in that situation, I should also should know that how much amount of water is getting into, because see, no, even though I place this sheet pile here, the water will be coming from the underground. Okay, water will come from the below this one. So I should know what is the amount of water which is flowing through the ground and coming into this one. Okay, if I know that, then I will apply some pumping arrangement here and take out the water outside this one. So to know that how much amount of water is flowing in, I should plot this flow net. So here, this is a head of water on this upstream side, and this is a head of water on the downstream side. So the head which will cause the flow is this much. So water will flow in this direction. So I had plotted the lines as a flow lines, okay, and then try to draw these dot lines as the equitation lines. So once I draw this flow net, I will be able to calculate the I will be able to calculate the amount of water flowing through the soil. So this is another flow net diagram for a dam section. This is another. See, this diagram is different. This diagram is different because there are two sheet piles provided on the upstream side and downstream side. So definitely diagram has changed. The equitation line has changed. Okay, here there is only one. So you can go through and study these all different type of equitation lines and flow lines, how it has been drawn. So this is another diagram where showing you the impervious bracket, and there is a filter on this side. Okay, these are double sheet piles, which shows again double flow lines. So once I draw this sheet piles, this flow net, I can draw measure the seepage through the particular media. Say this is for the dam. This is a soil mass, and the water is retained here. So the water which is retained here will pass through the body of the dam, and how the water is taken out, that is another important aspect. So this rock toe we are providing here to support the foundation. So we try to put all this into the rock toe so that the drainage will take place properly. So once I draw this flow net, I can plot, I can calculate the seepage to the foundation or body of the dam. Okay. So there are different, depending upon the type of the dam, the flow net will change. So there are different methods to plot it: graphical method, soil model, solution, Laplace equation, electrical analogy methods, and plastic models. So we'll just go by characteristics. The flow lines are always normal to the constant head. Equitation are always parallel to the constant head boundary. Flow lines are always parallel to the impermeable boundary. This is understand. You understand this? That flow line is always parallel to the impermeable, and equitation lines are always parallel to the constant head border lines. If you're able to find out these two locations of flow lines and the equitation lines, then it will be easy to plot this flow line. And these are the flow lines are perpendicular. Flow lines and equitation lines are perpendicular to each other. The another beauty of this flow net is all the net which are forming having the shape, the square shape, and we try to put a circle which will fit into that particular square. So that plotting the flow net is a trial and error method, and hence it depends how we can evolve it. So once I plot the flow net, I should know gradient. What is the gradient? Delta H upon delta L. That is, see, between these are the equitation line. Equitation line means the pressure all along the pressure all along this line are same. Okay, so equipotential line. So this single green line have the same pressure. So whether I measure here, whether I measure here, I will get the same pressure. So difference between these two gray lines will give the head loss delta H over how much length? Over this weight delta L, and hence I is equal to delta H upon delta L, which is the width of this flow net, and this delta H is what? The H is the total head loss. This NE is number of equipotation lines. How the total head loss is taken place over say 10 number of equipotation lines. So there are 10 equipotation lines. So that total head divided by NE will give me this small delta H. Then flow per channel is Q is equal to K into delta H into delta L into A. So I will put all these values. The total flow will be equal to this equation. You have to remember that total flow through your flow net, total flow through your flow net will be Q is equal to K into H into A by B into NF upon NC. This A is what? The other dimensions of your square. And I said the flow net, all the squares are square, and hence this will be same. So that is given K into H into NF upon NC will give you the Q. So number of flow lines, number of equipotation lines, hydraulic head which causes the flow, and the permeability. If you know, you will get the discharge Q. Okay, so for compacted embankment, I can find out this K in the laboratory. I know the head, I know the number of flow lines and channels, so I can calculate how much amount of water will flow through the body of the dam or foundation of the dam or through base of the sheet piles and so on. So this is very useful to understand this one. Okay, so these are the chapters which we have learned. The next chapter is about the compaction. This is a very simple chapter. We know why we need to know the compaction. Suppose I had to construct the road embankment, I had to construct the railway embankment. What I do, I excavate the soil from one location and put it on the site. Now, if I place the soil as it is, definitely it will be not in the compact state. Okay. Now, how much compaction shall I do? Whether just I place it and do something, elephant will, I will run the elephant over it, it will be compacted. Okay. But scientifically, you should able to know to what extent I will be able to compact the soil and how I will check that the soil is compacted, because the other property of the soil is depending upon these compaction parameters, whether it is strength, whether it is a compressibility, whether it is a permeability. All these properties are depend upon the compaction. And you know, the strength is a prime parameter for embankment, because otherwise the embankment may fail. And hence, the soil should be compacted to its maximum extent, because everyone has maximum capacity. Similarly, the soil has its maximum capacity to compact. So I have a task to identify that extent to which I can compact the soil. Okay. So to identify this one, we are finding out two parameters. One is called maximum dry density, that is called as MDD, and the other parameter is the optimum moisture content of the soil. Now, what it means, suppose if I compact dry soil, I will get X density. If I put some water into it and find out density, I will get Y density. Again, I will put water, Z density. Again, I will put XY density. Okay. So you will see the changes in the density of the soil with the presence of water at different percentage. So the scientific study has shows that the increase the dry density of a given soil is increased up to certain level of water content, and then it start reducing after that water content level. So the maximum density at a particular water content which we calculate, that density is called maximum dry density, and the water content is termed as the optimum moisture content. So our aim in understanding this is decimal only. So what compaction will do? Compaction removes the air, and compaction removes the air, and we compact more solids into a location. So there is another method called as a consolidation. In consolidation, this water is removed. In consolidation, water is removed because consolidation process takes place only when the soil is saturated. That is, no air remains there in consolidation process, and hence in consolidation the water is moved out. But in compaction phase, water is not moved out. Only the air is reduced. So we try to remove the air from the soil and bring all the particles closer to each other. Reduce the void ratio, reduce the settlement, volume change, increase strength, bearing capacity and is increased, permeability will be reduced, and liquefaction will also be reduced. And stability of the structure will also increase. So these are the purpose of compaction. So this is what I said. As I see, this is a plot with water content on x-axis, dry density on the y-axis. If I go on adding water, the dry density has increased and then reduced. So if I draw a curve to this, and this point, which see exactly we will be unable to find out what is maximum value, and hence we try to draw a curve which shows the lower limb and the upper limb of the curves, and we try to say this is the MDD value. This sorry, this value is your MDD, and this corresponding value is your OLC. Okay, so this curve is plotted, the maximum density and optimum moisture content is plotted. Now, this MDD or optimum moisture content varies with the type of soil, whether it is a clay soil, whether it is a silty soil, whether it is a sandy soil, plastic soil, lower plastic, higher plastic soil. Depending upon that, the MDD OMC curves also changes. So I am showing you these different type of curves. Say when we have a low plasticity index, sandier soil, so we are getting the MDD on the higher side of 17 to 22 kilogram per cubic meter. For intermediate soil, intermediate plasticity index, the soil we are getting MDD as 15 to 19, and for low higher plasticity index, we are getting the clay soils. So we are getting the MDD as 12 to 15. So depending upon sand, intermediate soil to clay soils, we are getting different type of density. The OMC, earlier we had seen the MDD. Now here OMC also, for when we have a coarse grained soil, we are getting the optimum moisture content very low. When we have clay soils, we'll get this optimum moisture content on the higher side. So this 8 to 14 is a percentage of OMC for low plasticity index soil or the sandier soil. Okay, this is 12 to 20 is for intermediate in this region. And for clay soil, 20 to 40 is your OMC value. 20 to 40 your OMC value. See, depending on the type of soil, we get the different OMC and MDD. And you should understood that sandy soil or the coarse grained soil will have a higher density, lower OMC. Whereas clay and the city soil will have lower MDD and higher OMC values. Now, we also trying to know that if all the voids are removed from the soil, what will be its density? This is a very hypothetical and imaginary state, because we will be unable to remove the voids, the air from the voids. Certainly there will be certain voids into the void, and there will be certain voids in the soil, and hence that condition will not be achieved. But theoretically, if I want to find out what is this condition, what is the water content at which I will able to attain this density where no voids will be available, I can find out by using simple equation. So I can draw this curve that indicate the zero void line indicates where zero voids are there and 100% saturation line. Because no voids, the water is filled with the all voids, and hence it is the saturation line. This curve shows maximum density can be achieved if all the voids are filled with water, there is no voids is left. And how can you calculate? By using this simple equation, gamma D is equal to G gamma W upon 1 plus WGS. Right. So I should know the specific gravity of soil, unit weight, and degree of saturation. Then I will get this gamma D value. So there are two tests, on the standard Proctor and modified Proctor test. Now these are Proctor test means we required some rod and all that. What we'll do, we take a volume, is a cylinder of 1000 cc volume, and fill the soil in it and compact the soil in different layers. Now this soil is compacted using a hammer, which is dropped from certain height. The hammer weight is for standard Proctor. The hammer weight is 2.6 kg, and drop is 31 centimeter or 310 mm. And there are 25 number of such blows will be taken there all along the surface, and it is filled in 3 layers. Okay, so we will note down the water content, note down the weight of the soil, weight of the weight of the moist soil, and we find out the water content, and then we can plot it. So compacted in that, and gamma D will be calculated. Once you know the bulk unit weight and water content, you can get the gamma D. So all these Okay, so all these will be calculated and we can plot it. This one. Now, as I said, we are compacting the soil in 3 layers. Each layer is compacted to 25 number of blows under the 2.6 kg hammer falling at the 310 mm. So that much, this definitely it means the certain compaction energy is used. So what is the compacting energy which has been used for this compaction can be calculated by the simple equation that how many blows are there per layer? We say 25 number of blows per layer. What is your hammer height? That is 31 centimeter. What is your height of drop? Hammer weight. Hammer weight is 2.6 kg and height of the drop is 31 centimeter and the volume of mold is 1000. So if I put all these values together for standard Proctor test, I get 592 kilojoules per cubic meter. I can generate a energy of 592 kilojoules per cubic meter for filling this one mold of 1000 cc. Okay. And then what I will do this, plot this curve and get MDDI OMC. See, this is your zero air wide line indicating, you understand the principle of zero air wide line. See, zero air wide line will always lie above your MDD OMC curve because say for this water content, at this water content, there is certain voids. So for the same water content, what will be the maximum density which can be observed is this much. Okay. So if I able to get this, if I able to find out that density, so this will indicate, this curve will indicate is a maximum density which the soil can achieve. This is zero error line. And modified Proctor test is similar to a standard Proctor test. Only, so these are the characteristics of standard Proctor test. The modified Proctor test will have 5 layers, 25 number of blows per layer, 5 layers, 25 number of blows layer. The hammer, it was here 2.6 kg. Here it is 4.9 kg. Drop is 310 mm and it is here 450 mm. So we are putting more weight, more drop. Definitely the compacting energy which is used for modified tractor is also more. It is around 2700 kilojoules per cubic meter, where it was 591 in case of standard Proctor. So around more than 4 times we are using energy for modified Proctor. Now, where we require standard Proctor and where we require modified Proctor density. The construction where which is impacted or which is subjected to a high load, say national highway. You have a village road, you have a national highway. Now, in national highway, definitely the truck which are loaded will be very heavy, and hence my road should be strong enough to sustain that much load. And hence I should compact that soil to its maximum density using this modified concept. As when I go for village road is subjected to a very small load, and hence unnecessarily I should not use the energy there to compact the soil to its very high density. Then I can go for a standard Proctor test. Okay, so depending upon the use, you have to decide whether you are going for standard Proctor or whether you are going for modified Proctor test. Say if you are doing construction of airport airstrips, okay, where your aeroplane landed, they took off. Now, how much dynamic force are exerting on that airstrips? Okay, so definitely my foundation should be strong enough to sustain those shocks, and hence I will go for modified Proctor. So choose your method depending upon the problems which you are facing. There are now 2 topics are left. I will go quickly, and another half an hour I will proceed. Then we can finish it. Okay, so 1 minute. So the next topic which will start is the consolidation. Now we have seen compaction, and in compaction, while studying compaction, I told you that this compaction will be compaction is achieved when I remove the voids. I remove voids in terms of only air. Whereas this consolidation process is also a compaction. The forces which are applied here are different than compaction process. So consolidation takes place with the removal of water, because this process will take place only when the soil is saturated. All the voids are filled with water, and hence consolidation is the process of compression of the settlement that undergoes as a response of placing loads onto the ground. Okay, suppose I had constructed this 10-story building here, and the soil is compressible. So after 10 years, the soil below your foundation may settle by say 20 centimeter, 50 centimeter, depending upon the load, depending upon the soil. And hence, beforehand, I want to know, before I construct this building, you should be able to find out what is the amount of settlement you are expecting from your building during the service life of that particular building. Suppose I'm expecting 50 years of life for a given building, I should calculate the settlement for this 50 years. So that settlement is maybe consolidation settlement, maybe a intermediate settlement. Now we know there are two types of settlements: primary and secondary settlement. The primary settlement is also again consolidation settlement and immediate settlement. Depending upon the type of soil, this also varies. Whether it is a coarse grained soil, whether it is a fine grained soil. In fine grained soils, the predominantly the consolidation settlement measures the amount of settlement. Whereas in case of non-cohesive soil, such as sand, the settlement occurs immediately after the application of the load. Okay. So if I constructing a building on the sandy soil, so the settlement will take place during the construction period itself, and the entire life there will be no settlement, further settlement. But when I'm constructing the building on clay soil, the settlement after construction will be very small, but it takes years together. It may take 100 years, 50 years to achieve certain amount of settlement, because you know the permeability of your clay soil is very low. So as I said, the consolidation taking place with the expulsion of water only. So that expulsion will take a longer period to expel that water completely through the voids, and then only the compaction will be achieved. Hence, consolidation is a slow process. It is a time-dependent process, and it's a static load application. It is not up due to the dynamic compaction. Okay, it's only a static load which is resting on the ground. That load is applied, and that is continuous process. Hence, this is a comparison of your consolidation and compaction process. So this is an okay. So this is an instantaneous process, whereas this is a time-dependent process. It takes more than 100 years to complete the 100% compaction, consolidation of the soil, applicable to unsaturated soil. Okay, the compaction is achieved only in unsaturated soil, and I said this consolidation takes place only in saturated soil. In this case, dry density increases and water content decreases. Here, dry density increases and water content does not change after a certain period. So this can be understood with this figure which I said to you. Suppose this is the soil mass. Okay, this is the soil mass, and these arrows are indicating the load coming from your building. So this soil is subjected to say a load Q. Q is the stress at this level, foundation level. Now, say this is a saturated clay. Now, this saturated clay, before I construct these structures, this soil is subjected to certain load, certain stress. That is the total stress. Then, when the load comes on the soil mass and water is unable to move out of it, unable to move out of the voids, then the pressure is exerted into the voids, and that we call as a pore water pressure. So you should able to find out what is the change in the stress because of the application of the sigma. You should able to know what is the pore water pressure changes. Okay, then you will be able to find out the settlement. Okay, now what is this? what is the level of pore water pressure or stress at particular level. We already also say that suppose if I find out this point A, this soil, the stress at this level is because of this overhead soil, overburden soil, and because of this Q well. Okay, so there will be two types of forces which are acting at point A. One is a overburden pressure, other is the surcharge Q which is applied there because of the structural load. Okay, so because say if there is no surcharge, this A soil, the soil at the point A is already compacted to a total stress, which is gamma into H. Because I am applying Q, because of this Q stress of additional coming up from the structure is applied, this Q is try to find out try to create a settlement in the soil mass. So I should find out that settlement because of Q value. So here it is indicating that is the condition total stress. Initially it is total stress. Now what is happening? This over the certain period of time, this pore pressure is reducing and it comes to a zero because the water is removing slowly water is removing, so definitely the pore water pressure is also removing. When the pore water pressure is removing, you see the settlement is continuously increasing. Pore water pressure is removing. What about effective stress? Effective stress is increasing. Why? Because I told you effective stress is a intercontact stress, that is contact between two particles are come together. Now as the water is removing from the soil, the particles are brought together. At one stage, when the total pore water pressure is removed, then all the particles will remain. Process are acting more, and hence when as the pore water pressure is removing, your effective stress is continuously increasing, and this effective stress is lead to the settlement. And hence, as this pore water pressure removes, the settlement is continuously. So this is the process, the fundamental concept of consolidation activity. Again, the same thing I'm putting in the different shape, that this soil which is subjected to Q load, has the thickness is H0, original thickness is H0, and original white ratio is E0. After say time period of say T is equal to 50 years, after 50 years, the load, say this Q remains same because we are keeping the same building, we are not changing the building. So this Q remains same. Okay, since the Q remains same, the load is there. After 50 years, what will happen? This soil of thickness H0 will be compressed to certain level, and this compression is a delta H. So delta H is the change in the thickness of the soil layer. Because the soil has been compressed or consolidated, the initial white ratio which was there, E0, will not remain same because your whites are getting reduced, and hence this E value which is there as a new value will be equal to E0 minus delta E, whatever the change takes place in the white ratio during the process of that particular consolidation. Using this thickness or the white ratio, what I can find out, the equation between these two, that delta H upon H0, delta H is change in thickness of the soil, H0 is the initial thickness of your soil layer, is equal to delta E upon 1 plus E0. So if you are able to identify what is the change in the white ratio, identify what is the change in initial white ratio, and you should know the thickness of H0, you can find out settlement of your formation. So this is a simple phenomena of concept of consolidation settlement. Now here I am just explaining two indices based upon the log E-log P curve. This curve is called a E-log P curve. That is, E is a void ratio, which is on the y-axis, and stress is on x-axis, which is in the log scale. So, as I said earlier, when the pressure is increases, the void ratio goes on reducing. Okay. So here, if you look at, initially this was the void ratio, this was the void ratio. Whereas the load is increasing here this side, so this void ratio is reducing, and I'm getting this curve. This is called as a E log P curve or and E log P curve. Now, depending upon the soil, it may be a single log compression curve, or it may be a segmental compression curve, like shown here. This is one straight line has come, and then again suddenly this strip has taken place. So, depending upon that, you get different compression index. So, I will get here one compression index and another compression index. Okay. Now, suppose I am compressed this soil. If I remove the load from the soil, then expansion will take place. So this shows the expansion curve. This shows the expansion curve, also called as a swelling index. But this expansion will not reach to its original void ratio because there are certain structural changes take place in the soil mass. Hence, we cannot go back to your initial void ratio. Okay. So if I want to find out this compression index, I can go take this equation that E minus E0 upon log 10 to the sigma bar upon sigma 0. And for expansion index also, I can get this one. Okay. So this ratio you can calculate. Now, you can also find out the coefficient of consolidation CV by using the one-dimensional consolidation test. Already I have shown you the approximate method for identifying the coefficient of permeability. So this was the same equation which I shown you earlier, that CV is equal to KB upon MU into gamma W. And I can put it in the other way, that this MV is a volume compressibility, can be taken as 1 plus E upon AV. So this is MV. This K and gamma W remain same. Okay. Now this time factor, that is how much time it will take to consolidate by certain amount, I can get by using the CV into T into HS square equation. Now this soil which is consolidated, that soil deposit can be termed as normally consolidated soil deposit, over consolidated soil deposit, or under consolidated soil deposit, depending upon how much stress, depending upon the stress to which your soil is subjected. Now, this soil which exists on the earth has been consolidated to a longer period of time. Maybe unknown forces at today we don't know, because this earth has in existence even more than 2 crores years. So we don't know what was there here at this place. So definitely this soil is got consolidated under certain pressure. If I am able to find out what is the pressure to which this soil is consolidated before I start my construction, that we call as the pre-consolidation pressure. Before we start construction, if you are able to find out the consolidation pressure, it is a pre-consolidation pressure. Now, so if I know this pre-consolidation pressure, and if I keep the same pressure on the soil, then it is a normally consolidated soil deposit. If I'm keeping the more stress, that will be over consolidated, maybe under consolidated soil deposit. And if I'm keeping the lower, that will be over consolidated soil deposit. So this pre-consolidation pressure can be determined by using Pusadkar procedure. Very simple. 1 minute, battery is low. I just put in. Hey, battery charger. कितना के बस एक 10 मिनट लो आवे त्याच्यावरती So I can plot this E log P curve and I can find out this pre-consolidation pressure. So this is a suppose E log P curve. I can draw these two lines, find out the point of minimum curvature, maximum radius, and from that I will take one horizontal line and draw a tangent at that point. Divide this angle into two half, okay, and draw the end tangent point, and then if I draw a point from this line, I will get this pressure. This is called the pre-consolidation pressure. Okay, so that way you can find out the pre-consolidation pressure. So this procedure is already explained in your books. Okay, now to find out the coefficient of consolidation, I have to conduct this consolidation test. That is a one-dimension consolidation test. I will just briefly and simply, very easy, simply I will say, explain how it can be conducted. Say this is a soil sample which is placed here. It is around 75 mm diameter soil sample, and this soil sample is placed under these sand beds. Okay, so the load is applied here, and I can find out how much settlement takes place of this soil mass. And as I said, the consolidation is very slow test. For actual soil may take 100 years together. Even for determining the coefficient of consolidation, I should require minimum 6 to 7 days for completion of one test, because I will apply one particular load here, note down the settlement to achieve complete consolidation under that load. Okay, so maximum it says there will be 0.01 divisions, 0.01 mm change in the dial gauge reading per hour. If it is not there, then I can go for the next load, or maximum 24 hours. So that various loads will be applied, so that various pressure will get, and various E value corresponding to that pressure will get, and then we'll plot that E log P curve, and we can find out coefficient of consolidation and other parameters. Okay. So this is a clay sample. This is a loading piston. This is a water squeeze. Consolidation is takes place because of the squeezing of water only. So we have to remove this water. Okay. Now, once I get different P values and different E values. Okay, void ratio. I want to find out the void ratio for corresponding soil mass. Okay, so that will be calculated. Estimation of coefficient consolidation. So there are two different methods. Once I get P and E, using that stress and void ratio, I can find out the CV by two methods. One is called log time method, and other is called height of solid method, or the square root type method. Okay. The E will be calculated by that height of solid method. Okay, or change in void ratio and height of solid method. So this CV from log time method is calculated. So this is your curve. So, E is on x-axis and log P on time is on y-axis, which is in the x-axis, which is in the log scale. This curve is plotted. Okay, this curve is plotted. Then you choose a time t1, time t at t1. You choose a time which is 4 times t1. Okay, and divide. Say whatever is this height, will take a height x above it, same delta E at the above. Okay, and draw a horizontal line. This indicate a zero consolidation. Then from here to here is a total consolidation. So we will put this as a 50% consolidation. Okay, 100% consolidation is taken as the intersection of the tangent point at the lower limb. Okay. So this point is in your 100% consolidation. So you get T50 from this curve. So the CV will be calculated by using 0.196 HS square upon T50. H is the thickness of soil sample. Okay. So from here I can get the coefficient of consolidation. There's another method of coefficient of consolidation, that is square root of time method. So on x-axis, I getting square root of time. That is time, how much time is required to consolidate. And on x-axis again, here it is E value. Okay. So what I required here for getting the CV in this equation is T90. That is the time required for 90% consolidation. So I have to find out that 90% consolidation, and here the principle which is used is this one. That it says first we draw this tangent line here. Another tangent line is a parallel line is drawn with the ordinate of 1.15 times of OB. OC is this. OC is obtained as 1.15 times of OB. OB is the tangent line which is drawn here. Okay, so we'll continuously draw this point and get this line AC, and the intersection with this wide ratio line will give me the point, and that I get the square root of 90, T90, and I'll find out T90 and get aggregate the CV value. Okay, so this is another method for this. So once I get the CC, the compression index from the E log P curve, I can calculate the consolidation settlement as using this equation. What is that equation? SC, that is coefficient of consolidation, consolidation settlement is equal to CC into SC upon 1 plus E0 into log of sigma 0 dash plus delta sigma dash upon sigma 0 dash. CC is a compression index, SC is the thickness of soil layer, E0 is initial void ratio, sigma dash is the initial total stress, effective stress, and delta sigma is the additional stress which is coming because of the construction of the structure. Okay, the CC can be obtained from your consolidation test. Also, it can be obtained from these two equations as 0.007 into WL minus 10 or 0.009 into WL minus 8. Okay, so once I know these values, I can calculate the consolidation settlement. The last topic which is there is the shear strength. Now, as we know, your concrete is strong in tension. Compression. Steel is strong in tension. Then soil is strong in which stress? That is shear strength. So intergranular friction which is taking place in the soil mass helps me in developing the strength. Helps me in developing the strength in the soil mass. Okay, and this intergranular stress which exists between this particle should be identified by a civil engineer, and the strength is a prime properties for identifying the strength of any structure, whether it is a dam, whether it is a building, a foundation, whether it is a bridge foundation, whether it is even slopes of your embankments. Okay, because the strength is the main parameters of the soil mass, and hence I should able to find out this strength in laboratory as well as in the field. How will I identify those? So first we'll see what is this, how the shear failure takes place. Say this is the two cases I'm showing. One is the foundation, and there is the embankment. Now this when the load is coming on this soil mass, this much soil is under stress condition. Okay, if the soil is not strong, what will happen? This soil will be moved away, and once this is moved, your foundation will be get tilted and your building will collapse. Similarly, in embankment, if the soil is not strong enough, what will happen? This will slide over it, and it is it will be collapse. Okay, so this strength is exerted all along this failure line. So I should able to find out what is the shear strength of the soil all along this failure plane. My shear strength should be more than the forces which is applied on the soil mass. If it is so, your soil will be, your structure will be safe and strong enough. That we obtained through a simple law which we know as the Mohr-Coulomb's law, and the Mohr-Coulomb law is designated by tau F is equal to C plus sigma tan of phi, where tau is the shear stress, C and sigma, phi are the soil parameters, sigma is the normal stress. So the soil, any soil parameters, suppose this is, I am considering, suppose if I consider this is one simple soil element, okay, this soil element will be subjected to these normal stresses. These are the normal stresses on all the sides of your element, and the shear stress along this plane. already you have learned this in strength of materials. So the same principal stress concept, principal plane, principal stress, Mohr circle are used in this soil mechanics also. So that is the shear stress applied. Okay, for finding out the stress at any particular plane, we can use that Mohr circle. Okay. Now this shear stress is correlated with the sigma by Mohrs and modified by the coulombs, and hence this curve is called as the modified Mohr-Coulomb's law, as equal to tau is equal to C plus sigma tan of phi, where this C is nothing but the intersection of this failure envelope on tau axis, and phi is the inclination of this failure plane, which is termed as a friction angle. So the C is represented as a cohesion and phi is represented as the angle of friction. These are the soil properties which relates to shear strength of the soils. So I should able to find out this C and phi value by any of the methods, and if I know the C and phi, I can get the shear strength, I can get the stability of any structure identified. Okay. Now the cohesion is particularly available for fine grained soils. Friction is available for the coarse grained soils. Suppose if I put C is equal to 0, this equation becomes tau is equal to sigma tan of phi. This is for purely sandy soil. As I said, C will be cohesion, which is available for only clay and silt. Okay, and if it is a pure sand, no clay and silt component there, so there will be no cohesion. So C will be 0. So when C is 0, the tau will be equal to sigma tan phi. Now, in other case, if my soil is purely clay soil, no sand particles are there, then phi will be 0. So tau will be equal to C. So tau F will be equal to C. Okay. So that you should understand basic principle of that one. In his case also, I had to understand the total and effective stress. Already I told you what is effective stress and what is total stress. That effective stress sigma dash is equal to sigma minus u. So if you know this pore water pressure, you can find out the effective stress. So if I draw a Mohr circle diagram for effective stress and the total stress, this will be the see the sigma v, which is vertical stress, the total stress. So my Mohr circle will be drawn here, and if I reduce by pore water pressure mu, it will be shifted backwards and indicated by sigma v dash. Okay, so this is the diagram which shows the effective stress parameters and total stress parameters. So when this firm line indicate this total stress condition where I'm getting phi value, and when I do the same conduct this same soil under the effective stress condition, I will get the phi dash. So the effective conditions will be developed by phi dash, indicated by sigma dash and phi dash, and this is indicated normal stress or total stress indicated by sigma and tan of phi. Now, the shear test which we are conducting for determining the strength or the shear strength, basically it depends upon what methodology you had adopted for consolidation and for applying the shear force, or applying the shear force. Okay, for determining the shear strength. Now, depending upon the consolidation of the soil mass and depending upon the water which is drained through it, we divide the shear stress test into three different concepts. One we call CD test, one we call CU test, other we call UU test. CD means consolidate drain test. CU test means consolidate undrained test. UU means unconsolidate undrained test. So first I will explain you UU test. Say I had taken a soil sample and just tested it directly. I had not applied a pressure to consolidate it. I had not allowing the water to flow through it. Because as you know, as the water is flowing through it, the pore water pressure will be reducing, the effective stress is increasing, total stress of effective stress is increasing. So I don't want to know what is my pore water pressure changing during the process. Simply, I will bring the sample, test it. That is unconsolidated undrained test. Then next test is consolidated undrained test. The soil sample which I taken from the field, now I am consolidating to a stress level to which your structure is going to subject. And I try to see that under that particular consolidation pressure, what will happen to the soil mass. Okay, so the soil is consolidated, but during shearing testing, I will not allow the water to drain out. Since I am not allowing the water to drain out, hence again pore water pressure is increases during the application of the condition. So that is a consolidated undrained test. And the third test which I can conduct is a consolidated drain test. Then it means the soil sample is consolidated and the water is allowed to drain during the shearing of the soil sample. So the drainage is allowed through this body of the soil sample, and it is subjected to that condition. Now, why I need these three different type of tests: UU test, CU test, and CD test. This UU test also called as a quick test. UU test is also called as a quick test because certainly I take the sample and test it, so fatafat ho jayega. Whereas in consolidated drain test, that is CD test, it is a slow process because I require time to consolidate soil sample. I required a time for testing also. The shearing is taken place in such a fashion that the machine is very slowly run, and it may take even 8 days to complete one CD test because the rate of shearing should be such that the water should be continuously removed from the soil. Okay, so why we need to conduct these three different tests? Because it depends upon what stability you are trying to understand, whether it is a short-term stability, whether it is a long-term stability, what structures you are considering, depending upon the importance of your structure. Say for dam, is a huge dam which is storing a large amount of water on the backside, and if I don't understand the properties of the soil much thoroughly, then if mishap happens, it will lead to a great extent, a great loss. Okay, so depending upon that, I have to conduct a particular test and get these values of effective stress parameter or the total stress parameter continuously. Now, there are different tests which will be conducted in the field as well as in the laboratory to find out the C value and the phi values. The most common tests are direct shear test, triaxial test, unconfined compression test, and bend shear test, which can be conducted in the laboratory. Okay, and as I said earlier, this is the sample which you take for testing very small, and hence if I want to find out in the field, I can conduct this vane shear test, tor vane, pocket penetrometer, fall cone, pressure meter, static cone penetrometer, standard penetration to get the shear parameters. Okay, so we will limit only to this four tests: direct shear test, triaxial shear test, unconfined compression test, and vane shear test. We quickly will go to these parameters. Okay, now in case of direct shear test, directly we are applying the shear force on the soil sample. Directly we are applying the shear force on the soil sample. How? So this is a box. This is in one line. The soil is filled here. I am applying the normal load on this side, and then the upper half is moved out. Okay, you can see slowly how it is moving out. The upper half is remain constant and the lower half is moving out. This is placed on the rollers. Okay, so this lower half is moving out and the shearing takes place along this plane. Okay, so we are trying to find out the stresses which are developed along this horizontal plane, and hence the biggest disadvantage of this direct shear test is that the failure plane is predetermined because the soil has to fail only along this horizontal line. The soil has to fail along only this horizontal line, and hence this is the biggest disadvantage of the soil. But this test is very simple, quick, and you can easily find out the C and 5 value. Now what we'll do, we'll apply certain pressure P. Okay, when certain pressure is applied, normal load is applied. Under that, I'd shear the soil sample and get certain shear strength. Okay, then again I will apply additional another load, another shear stress. So likewise, I will get few points. Say the sigma will be here and tau will be here. Okay, corresponding to normal state, what is your shear stress? And if I join all these lines, I will get the Mohr Coulomb's envelope. And from that, I will get, suppose if this brought it back, so I can identify the C value for this value and the phi value with respect to this inclination angle. So it is a very simple test. This is the normal equipment which you might have seen in your laboratory for finding out the direct shear test. Okay, so this is the procedure for every normal system. Sigma 1 is applied, sigma 2 is applied, sigma 3 is applied. We will be getting this curve, shear displacement versus shear stress, and we will find out what is the maximum value of shear stress. And those tau F1, tau F2, tau F3 will be calculated and just plotted normal stress versus shear stress, and you can get this phi value. It is passing through origin, or if I'm getting a curve like this, I will get C value and phi value. So this is simple normal shear. Now, for two soils, we'll see how these change strength take place. Okay, so this is for sand, stress strain relationship for the sand. Now, sand may be loose, sand may be dense. How your shear displacement varies with the shear stress and what changes takes place in the soil during the shearing, that also we can see. Say, loose sand. Okay, this is okay. This is a blue one is a loose sand, cover for the loose sand, and this one is for the dense sand. Now, if you look at the shear stress is increasing in the loose sand, whereas in dense sand, the shear stress increases maximum and then sharply down it. Similarly, if I see the change in the volume of the soil mass in loose sand, or normally considered sand, the volume is continuously decreasing. Volume is continuously decreasing. Whereas in case of dense sand, the volume decreases and then suddenly increases. So why it is happening? The fundamental principle is, see, in loose sand, what is loose sand? The soil is very loose. Loose means void ratio is more. So when I'm applying the load, what will happen? The soil particles are getting adjusted within the voids. Okay, and since they are getting adjusted the void, the compaction of the soil mass takes place and the volume is getting reduced, continuously is getting reduced. Whereas in case of dense sand, initially with a certain pressure, the soil is getting compressed in the voids which are available. Okay, after certain amount of pressure, there are no remains of voids and the soil is unable to accommodate that stress within its volume. Then what will happen? It try to push out the soil mass, and hence the expansion takes place in the soil during the testing, and hence we can see this curve of volume change in the dense sand. In case of clay, if I go for the stress versus normal stress concept, for normally consolidated clay, effective stress condition, the C dash is 0. For that is cohesion. See, I said earlier, for cohesion is for clay soil, but depending upon what conditions you are subjecting, your C value and phi value will vary. Okay, so in case of normally consolidated clay, C dash remains 0, and for over consolidated clay, C dash will not be equal to 0. So we will get certain value of C dash in over consolidated. Say again the same reason. So other test is a unconfined compression test, is a simple test. Here what we do, you place a soil sample here and apply the load, note down the settlement and the loading condition and find out the strength. This is a E log P curve, which is plot, not E log P, stress versus strain curve, which is plotted, and find this maximum value. This maximum value, that is QU, is unconfined compressive strength, and this unconfined compressive strength will give you the cohesion value Cu, that is called undrained cohesion or unconfined compressive cohesion, which is equal to Ku by 2. Now, only thing you have to apply here this correction area while calculating the stress, because when I apply, suppose this initial sample is this much, this is the size of the sample. During application of the load, the soil getting the volume is increasing. Okay. Now the cross section area of the soil sample is increasing. When my cross section area is increasing, the stress should be reduced. So I have to find out this corrected area and corrected sigma, and then only I have to plot it, and then I get the QE value. So this was a simple unconfined compression test. Now the third and important test which is calculated is for important positive we calculate, we use is a triaxial compression test. Now this name itself indicates you that the stress is applied in the three axes. This is one plane, this is another plane. Okay, suppose if I take a cube, so this is x, y, and z. In all the three directions, the stresses are applied. Hence, it is called a triaxial compression test. So this is and this by this test I can find out. I can conduct CU test, CD test, and UU test. All the type of tests can be conducted depending upon your requirement. The simple case is that I have to prepare a soil sample, place it here, fill it with the water. This sail is filled with the water, and I apply the lateral pressure on this sample. This test is more reliable because we try to simulate the same stress condition as in the field. Say this is a ground level, okay, and if I collected the soil sample from this location. Now this soil sample is subjected to this much overburden pressure of the soil above, and also a lateral pressure from the surrounding soil. So in unconfined compression test, this lateral pressure is 0. So we are not getting the lateral pressure, and the soil is not subjected to pressure which is available in this. Say if you are standing in the ground, what happens? You are getting compressed by all surrounding peoples. Similarly, the soil element which I am looking at the ground, below ground level, is also subjected to such a stress that we call as the lateral pressure. Okay, and hence that lateral pressure is applied here. The lateral pressure is applied and normal pressure is applied. And this lateral pressure and normal pressure applied will be used for calculation the value of C and phi. Okay. So what type of test I can conduct? I can conduct CD test, I can conduct UU test, I can conduct CU test, only depending upon consolidation and drainage condition of the soil. Now, in the triaxial test, again, what I will measure sigma 3 and sigma 1. So sigma 3 and sigma 1 is calculated because sigma 3 is a applied vertical normal stress and sigma 3 is a lateral pressure. So both the values are known. So I will draw this Mohr circle, and tangent to the Mohr circle is drawn. I will get the phi value. Suppose this tangent is going this way, so I will get the C value at this location and the phi value at this location. The correction here also I have to apply the correction to the area for getting the value of stresses. So A equal to A0 upon 1 minus psi z. So this was the CD test where C is 0. This was the CU test where I can get CU and C for effective stress and total stress. Okay. So, the other test is a bend shear test. Now the same, this test is very applicable only for the cohesive soil, such as the clay soil. And this test is necessary as a quick test. It's a quick test. Okay. There is a simple thing. The simple principle is that the 4 blades. These are the 4 blades which are placed perpendicular to each other on this rod. And this yellow one is complete. This is the soil mass. So if I immerse this blade into the soil and by some mechanism I am able to rotate, what will happen? These edges will try to shear off the soil here along this plane. So what is shown here, these are the plan. So when I am rotating it with the help of the torque applied, it will shearing the soil. Okay. So we will try to measure a torque which will make the soil failure. Okay, so the rotation is applied at the speed of 6 to 10 degree per minute, and we try to measure that torque. Okay, so this is a simple unit which is used for calculation of the torque, which is K into theta. Once I get this T, I can calculate the Cu by measuring T upon torque upon pi into dq h upon 2 plus d cube upon 6. And there are two mechanisms. One is when both the surface takes part in the shear. That means this this top of the vane and bottom of the vane takes part in shear. That equation will be used, and only see in shear test, when shear test we have to keep minimum 1 centimeter depth. Okay, then only this top and bottom portion will take part in shear. If the cover of the soil above this top of the vane blades is very small, then it will take only the bottom surface of the vane blades takes part in shear, and that the equation has changed to d cube by 6 to d12. Only this is the change which is taking place, and then you get directly the cohesion value of the soil. Based upon this test, a pocket vane meter has been developed, which will be used for finding out the field cohesion of the soil. Clay soil. Clay soils are very sensitive. They change their strength depending upon the disturbance which are caused to them, and hence, for getting the accurate value of the existing in this field, and you should go for this pocket venitrometers, and that can be calculated. There is one point that is called a stress path. How your stresses are increasing and what is the path followed by that particular stress is called a stress path. A stress path is a plot between sigma and tau. Sigma is on x-axis and tau is on y-axis with the progression of the points representing the loading process of the soil sample. Okay, so suppose if I apply this is sigma 3 and this is sigma 1. If I apply this much load, this is the maximum load is applied here is a B. Maximum stress which is applied here is B. Again, sigma, I keep the same sigma 3 and only increase the sigma 1. Because in shear stress also we had seen we are increasing sigma 1. Okay, so I will get this point C, point D, point E. So this, if I join all these lines, this indicate my stress path. So this is a path which will be followed by the soil mass during application of the stresses, and which show the maximum point which are existing on that particular points. So that is a simple. This stress path is useful for finding out useful for finding out the settlement of the soil mass. Okay, I think this is the last point. Thank you all. Sir, are you there? If you have any doubts, you can ask me.
Hello?
Hello.
Hello?
हाँ आवाज बार कमी येतोय.
आवाज समजत आहे का सर?
हाँ कमी येतो. हाँ बोला ना.
हाँ. Any question, student?
Just ask them. If you have any doubt, they can ask me.
Any question?
So I don't think
any queries, student? कोणाचा क्वेरी नाही आहे वाटते.
असं वाटतंय. असेल नंतर त्यांना काय असेल तर त्यांना सांगा मला. काही प्रॉब्लेम नाही. विल सॉल्व.
हाँ सर, कोणी क्वेरी नाही. हेलो.
हाँ सर बोला सर.
हेलो.
हाँ हॅलो.
हेलो.
हाँ ऐकू येते सर. हॅलो हॅलो ऐकू येते तुमचं ऐकू येते बोला हा बोला बोला बोला
हॅलो
हा हॅलो हा सर बोला ना हा सर
हॅलो
हा सर
आवाज
ऐकू
येतोय
येते
का?
हो येतोय
सर आवाज येतोय का?
होय किंवा व्हिडिओ बंद करून टाका म्हणजे आवाज येत जास्त सर काय बंद करायचं तर तुमचा आवाज क्लिअर येत नाहीये फक्त हॅलो
हा सर आवाज येतोय का त्याचा?
तुमचा आवाज थोडासा मध्ये मध्ये कमी जास्त होतोय
इकडे कव्हरेज
हा ठीक आहे ना तर काही प्रॉब्लेम असेल तर तुम्हाला शाल वी एंड
सर
ओके थँक्यू
हॅलो
हा सर